Check out this proton that I have here in the center of the page. I'm going to start by drawing some E-field lines around it. I know that the E-field will point out from a proton. The way I can tell that is I would put a small positive test charge somewhere in space, like right there, and I know that that small positive test charge would feel a force in that direction. So the E-field lines look something like that for this proton. Cool. Now, I want to define something for you, and that thing is an equipotential line. What those are lines that define where equal potential is in space. So all of these points along this circle have the same potential. That's not electric potential energy, this is potential, and I could label that V1. All of these points in space, notice that these should be circles. I'm trying my best. V2, all of these points in space have the same potential as well. Remember, I could write a little note for the potential of point charges, that is KQ over R. All of these points have the same R. So it makes sense that all of these points, this would be R1, that would be R2. It makes sense that all of these points in this circle have the same potential. Oh, hopefully this makes it. Oh, make it. That's V3. Okay, a couple things to note about equipotential lines. One, I'm running out of space, so I'm just going to have to do this over here. The E field points from high to low potential. From high to low potential. Meaning that here I have some potential V1, and the E field is pointing in this direction, and V1 is greater than V2. V1 is greater than V2, which is greater than V3. That all makes sense with our potential for a point charge equation. As R gets bigger, as we get further away from this proton, V gets smaller, so V1 should be greatest and V3 should be smallest. Another thing to note, well, I already said this, all points on V1 circle have the same potential. And that is the very definition of an equipotential line, lines that show equal potential everywhere. The last thing to note is that the E field is perpendicular to equipotential lines. Okay, check this out. I've got my E field lines in pink. I've got my equipotential lines in green. And these two lines are perpendicular to each other always. So let's look at something that's not a point charge, shall we? Okay. Here I have equipotential lines continued. Let's just say that I have these potential lines. Let's call this positive 20 volts, positive 10 volts, 0 volts, negative 10 volts. Remember that we are free to define what is our zero voltage and then go from there. So let's say that I have an arrangement where those are my equipotential lines. Okay, we could then find the E field at any given point. So let's say I want to find the E field at that point in space. Well, I know two things. One, that the E field points from high potential to low potential. So it's going to go in this direction. Secondly, I know that the E field is perpendicular to the equipotential line. So that's my E field at that point in space. What about this point in space? It would look something like that, from high potential to lower potential. What about at this point in space? Something like that. Something like that for that point in space. If I was checking out a proton right here and I wanted to know which way the force would be felt on this proton, well, I know that the force would be in the same direction as my E field for a proton. And if I was checking out maybe a negative electron charge here, I know that the E field is pointing in this direction right here, but since I have an electron, it's going to feel a force in the opposite direction, so the force on this electron would be something like that. Okay, that's it for now in equipotential lines. Hope you learned something. I will see you soon.